Hi everyone! Today we'd like to highlight key features of 2.5 release and how to get most out of them. Let's review new features and improvements one by one. Before we proceed, we'd like to note that the video description contains time anchors to specific features discovery, so you can quickly jump to a particular feature description or easily find info about them later. Now let's proceed to the first feature, JSON support. We've finally added support of JSON data structures to telemetry and attributes API. Many thanks to our community for suggesting and pushing this feature through GitHub issues. JSON support allows you to both upload from device and push to device nested objects. This feature is available for all transports and integrations, so you can use it with Device Connect over HTTP, CoAP and MQTT, and with various integrations available in ThingsBoard Professional Edition. The idea behind implementing this feature is to simplify work with device configuration. You can store one configuration JSON as a shared attribute and push it to the device. Thus, no need to store separate attributes. You can also process the JSON data in the rule engine, raise alarms, etc. Such improvement also minimizes the number of database operations when ThingsBoard stores the data. As you probably know, temperature and humidity from this message will be stored as a separate rows in SQL or NoSQL databases, in order to efficiently aggregate this data for visualization. But we don't need to aggregate JSON data, so we can store all the configuration content as one row instead of separate rows for each configuration item. To give you a clue, in some of our environments we decrease the number of database operations more than 10 times by aggregating multiple parameters within one JSON. You can find more info on how to use this feature in our API documentation. Let's proceed to the next feature, time series storage improvements for SQL databases. In order to achieve new improvements, we were forced to update the minimum required version of PostgreSQL from 9x to 11x. The upgrade instructions for ThingsBoard platform contain useful links on how to upgrade your Postgres database as well. Partitioning of time series data in Postgres. So, we've introduced partitioning of the time series data into partitioned tables. This simplifies same administration tasks of dropping the old data. Now this operation is much more efficient. The partitioning is configurable using this property from ThingsBoard YML or this environment variable that may be set in ThingsBoard conf or Docker environment file. By the way, we do recommend to use environment variables wherever it's possible and stop using the YML file, because once the structure of the YML changes, troubles during the upgrade to the newer version may appear. This feature also helps to minimize the impact of huge tables on performance of the inserts to the database. On average physical servers with SSD disk, we have achieved constant performance of about 40,000 operations per second without any database tuning. Configurable TTL implementation for telemetry and events. Next improvement is an automatic cleanup of all telemetry for PostgreSQL database. This feature has existed in Cassandra for ages, but in Postgres there is no time to leave or TTL. We've added a service in ThingsBoard to periodically clean up the database. This service cleans up two largest tables, events and TSKV. Events table contains debug events and other statistics, so you can configure separate TTL for debug events and separate TTL for all other events. The TTL parameters measuring units are seconds. Similarly, you can configure the TTL parameter for time series data. Please know that the TTL parameters you see here are system-level parameters. They are default, but you may override them for specific tenants or specific customers. In such a case, you need to set the TTL attribute for a specific tenant or customer. The value is also in seconds. Pay attention, zero value in TTL means that the data is stored forever. And be careful with this feature. We recommend setting up a daily backup procedure before configuring the TTL. Wrong configuration may lead to permanent data loss. You may find backup instructions by following the link in the description or as per request to our Contact Us form. Next feature: reduce size of telemetry tables on 40%. We were able to reduce the size of the telemetry database table by about 40% due to implemented optimizations. We added the vocabulary of data keys and removed some columns which can be derived from entity tables. The upgrade to the new structure is completely automatic, but the duration of the upgrade depends on the database size and database server performance. The upgrade of 10 GB takes approximately 1 hour. Do not hesitate to ask your questions and comments to this video on ThingsBoard YouTube channel. Let's proceed to next big thing: OAuth support. With ThingsBoard 2.5, you are able to configure single sign-on using OAuth 2.0 protocol. This means that now you don't need to ask your employees or customers to maintain a separate account on ThingsBoard. They can log in with one click. ThingsBoard provides extensive configuration parameters to integrate with any identity provider that supports OAuth 2.0 protocol. We've covered 2 examples in our documentation, Google and Auth0, but we plan to add more guides with other identity providers quite soon, for example Azure Active Directory. It's worth noting that you may configure multiple identity providers to be active simultaneously. Let's quickly review the process of adding SSO to your ThingsBoard instance. Step 1. Enable OAuth 2 by setting security OAuth 2 enabled parameter to true in your ThingsBoard conf file. Step 2. Choose your identity provider and generate OAuth 2 client ID and client secret. There are plenty of tutorials on the web on how to do this. Those tutorials also provide other static configuration parameters you will need. For your convenience, we plan to add guides to the most common identity providers and constantly improve them. Step 3. Final and probably the most important step is to configure mapping between the information from identity provider and ThingsBoard user. There are several important parameters. Allow user creation. This parameter controls ThingsBoard behavior if provided the user doesn't exist in ThingsBoard. By default it's true, but you may disable it. If disabled, only pre-provisioned users will be able to log in. Activate user. Activate user controls whether the user will be able to set a separate login and password after successful login. If yes, the user will be able to define a password and login without SSO. This may become a security issue, so we disable it by default. Type of the mapping. Basic mapping is sufficient for most of the cases. Custom mapping allows you to define a separate microservice to replace basic mapping features. We will cover custom mapping in a separate video. Let's concentrate on the basic mapping for now. So, basic mapping defines how to convert the user object provided by identity provider, for example Okta or Auth0, into an object ThingsBoard understands. Essential property that ThingsBoard requires is the email of the user that should be unique per ThingsBoard instance. Email is usually present in the info from identity provider, so we can configure email attribute key to email. Now, when we know the user's email, we also need to understand which tenant this user belongs to. This is done using tenant name strategy, which is either to use the domain name from the user's email itself, or some other field from the message by using the custom strategy and some keys from the incoming user object. If the mapper finds out that the tenant name doesn't exist in a database, it will create a new tenant. Similar functionality is available for customer name. Let's have a brief look for a few examples. If we use the domain tenant name strategy, we can add all users with the same domain to a new or existing tenant. This is convenient if you want to group all users into tenants by their domain name. If we use email strategy, then for each user we'll create a separate tenant. This is similar to self-registration feature. If we use custom strategy, we can mix and match various combinations of tenant and customer names. For example, you can configure which tenant and which customer this user belongs to. For the professional edition, you can also configure the sub-customer scenario, meaning that if the customer name is not found, we'll create a customer as a sub-customer. The name of the parent customer will be taken from parent customer name pattern. User group name pattern is also specific to professional edition. We'll automatically assign the user to certain groups using this pattern. You can separate them using comma. Few more practice. Let's assume our ThingsBoard instance is responsible for HVAC monitoring in the office facilities for a big international company. In this case, we have two company branches in the US and Canada. Each branch has regional offices. You want each office to be a sub-customer inside the branch customer. Now, there are two roles, manager and worker. Manager will be the customer administrator, while workers will be regular customer users. The following object is provided by identity provider. Now the following mapping is applied. As a result, when the manager logs in, he will have full access to the sub-customer user. When a worker logs in, he has read-only access. Sometimes the functionality of the basic mapper is not sufficient and you need to do more actions when the user logs in. This is important for cases when you need to create some entities for new users on the background, or have very complex mapping, or want to trigger something else. In this case, you can use custom mapping. You will need to supply a URL of the microservice that will be invoked each time the user logs in. The result of your microservice invocation should be the same OAuth to user object. Your custom microservice may use ThingsBoard REST API to manipulate ThingsBoard entities under the covers. One of the most significant news in version 2.5 – support of new message queues. Starting version 2.2, we support Kafka as a main message queue. Kafka is a great, widely used system and we love Kafka. However, in some cases, usage of the managed queue service makes more sense than hosting your own Kafka service. For example, for environments with low message volumes but sensitive to data loss, this can be the case. Most likely, even if you have 1 million messages per day, it's still cheaper to use a managed queue instead of hosting your own Kafka servers. Since version 2.5, when you have 1 million messages per day, you can get a reliable and durable messaging solution for approximately $1 per day, and you don't need to worry about the downtime, maintenance and support of your message queue. That said, we decided to add support of AWS SQS, Google PubSub and Azure Service Bus. Those are managed messaging systems from the biggest cloud providers. The list of supported systems and cloud providers is going to be extended in the future releases. Please add the queue implementations that you would like to see within later releases to the comments or create a GitHub issue. Now, what if you'd like to host everything on premises and for some reason don't want to use Kafka? In this case, we have also added RabbitMQ to the list of supported systems. So, if you scale to millions of messages per hour, Kafka quickly becomes quite an obvious choice for the majority of the environments, especially in terms of cost efficiency. If you have much less messages, you can use any of the systems listed above depending on your company policy or cloud provider. Finally, let's proceed with the review of the rule engine improvements. One of the main improvements is support of the back pressure logic. The motivation is quite simple. Before 2.5 version, the rule engine was polling as many messages as possible. This was working fine for the most of the cases, but the rule engine was affected by the peak loads. Back pressure helps to protect from such cases. The platform is processing as many messages as possible and uses message queue to store unprocessed messages. So, if devices generate more messages than the system can handle, those messages are stored in the queue. If this is a peak load, those messages will be processed with some delay. If the load is growing organically, you will be able to add more rule engine services to keep up with the load with no downtime. With the new implementation, rule engine pulls a certain number of messages from the queue and creates a message pack object. Next, the rule engine service starts processing of the messages from message pack using the rule chains. Once the rule chains successfully process the messages, they are acknowledged, and the new pack of messages is going to be processed. Back pressure corner cases. This sounds quite simple, but let's deep dive into a few problems. How does the rule engine decide when the message is processed? What if the message processing fails at some point? What if the message processing is taking too much time? And how to control the order of message processing? Message processing case 1. How rule engine decides when the message is processed. First of all, the message processing may be either successful or unsuccessful. In the simplest case, the message is processed by the rule engine until it reaches the final rule node in the chain. If the final rule node successfully processes the message, it's marked as processed. If the final rule node fails to process the message, it's marked as failed. We'll learn more about how to deal with failed messages later in this video. Now let's review some other successful cases. Case 2. You may use the acknowledge node to mark messages are acknowledged for the message queue. In this case, rule engine doesn't track what happens to the message next. This is useful if you have some critical processing logic and some experimental processing that may fail, but you don't care about this. Another case. Rule engine will split the message into two copies if one particular rule node has two outbound relations with the same relation type. In this case, each copy has a unique message ID. All other message fields are the same. Those copies are pushed to queue first. Once the queue acknowledges the push for both messages, the original message is immediately marked as acknowledged. Queue processing strategy. We've just learned when the message is marked as processed or acknowledged. Now let's figure out what's done with the failed messages. ThingsBoard 2.5 introduces a new configuration parameter called queue processing strategy. Processing strategy controls how failed or timeout messages are processed. There are 5 available strategies. Skip all failures. Simply ignore all failures and timeouts. This will cause messages to be lost. If database is down, the messages will not be persisted but will be still marked as acknowledged and deleted from the queue. This strategy is created mostly for backward compatibility with previous releases and development or demo environments. Retry all. Retry all messages from the processing pack. If one of 100 messages will fail, strategy will still reprocess. Resubmit to the rule engine all 100 messages. Retry failed. Retry to process all failed messages from the processing pack. If one of 100 messages will fail, strategy will reprocess only one message. But in this case, timeout messages will not be reprocessed. Retry timeout. Retry all timeout messages from the processing pack. If one of 100 messages will timeout, strategy will reproduce or resubmit to rule engine only one message. Failed messages will not be processed. Retry failed and timeout means retry all failed and timeout messages from the processing pack. And the all retry strategies support important configuration parameters. Retries, number of retries when the 0 means unlimited. Failure percentage, skip retry if failures or timeouts are less than certain percentage of messages. Pause between retries. It refers to a time in seconds to wait in consumer's thread before retries. We've prepared a new guide that explains how to use message queues for message processing. Please see comments to the video or use this pop-up link. One queue is not sufficient. We've just learned how to configure the rule engine to reprocess failed or timeout messages. It's very important to understand that messages are grouped in packs and the processing is going pack after the pack. So, assuming you have configured retry failed and timeout processing strategy with unlimited retries, you will block processing of new message packs if the previous one is failed to process. But what if some messages are more important than other ones? Let's review the practical use case when you receive a telemetry stream and create some alarms based on certain conditions. Imagine you receive 1,000 messages per second and raise one alarm on average. Once the alarm is raised, you'd like to send it to the external system. If your external system is down or overloaded, this will cause a bottleneck in processing of main message flow. What if you don't want to block main message processing, but you want to retry some very important messages? You cannot define multiple processing strategies for one queue, so obviously one queue is not sufficient to cover all of the cases. ThingsBoard 2.5 comes up with an out-of-the-box solution. Rule Engine supports multiple queues. Each queue may be configured to use a different processing strategy. At the moment, all configuration is done in ThingsBoard YML or using environment variables. Note that we plan to implement UI for queue configuration for system and tenant administrators in 3.1 release. Submit strategy. Processing strategy helps you to control failed or timeout messages and reprocess them within the message pack. Now we'd like to highlight one more configuration parameter of ThingsBoard queues. Submit strategy defines processing order of the messages within the message pack. The default strategy is burst, which means all messages are submitted to the rule chains in the order they arrive. Similar strategy is batch. Basically the same as burst, but messages are grouped into batches using batch size parameters. This is useful to control load to external systems. For example, your external system has a REST API and you want to invoke it when a new message arrives to ThingsBoard. If you know that the external system can't handle more than 100 parallel requests, you may use batch size equal to 100. Unlike burst and batch, ThingsBoard also provides sequential strategies, meaning that the messages are grouped by some key. The key may be device ID, we call it originator ID since the message may be processed not only by device but also from alarm or other entity. Alternative key is tenant ID. Also, we can just process messages one by one, which is basically the same as batch strategy with a batch size set to 1. Default queues. We'd like to highlight several pre-configured queues that are available by default. You may completely reconfigure those queues, but you shouldn't rename the main queue. The queues that we have configured are sufficient for most of the simple cases. However, if you have a lot of processing steps, you may require more queues to isolate those steps. This heavily depends on the use case.